This is your presenter Asloob Mudassar, and I am presenting slide number 112 of the course on laser physics. Question is, in continuation of question 111 or slide number 111, discuss the threshold conditions for space independent rate equations for a quasi 3-level laser system. The answer is, for threshold inversion, we set d phi over dt is equal to 0. That is the change of phi, that is phi is constant and phi is the number of photons in the cavity. So we need to put d phi over dt, that is the time derivative of phi with respect to time is 0. We have to set this one in equation number 8, which gives this. So let me show you equation number from the previous slide, that is equation number 111.8. This is shown in appendix. So this is equation number 111.8. d phi over dt is equal to VA into sigma E into C over capital V multiplied by N minus 1 over tau C. This is contained in the square bracket, and outside that one we have phi. So you need to set d phi over dt is equal to 0 in order to find n. So you need to solve the value for the value of n, which will give you then the threshold value or the critical value. So setting that one derivative equal to 0 in equation number 8, 111.8, we get NC is equal to capital V over VA into sigma E into C into tau C, and this is equal to gamma over sigma E into L. The right hand side gamma over sigma E over L is written where we have used 1 over tau C is equal to gamma times C over L naught, and V is equal to L naught over small l. This whole bracket parenthesis is multiplied by VA. These terms have been defined in this paragraph. That is, capital V is the mode volume within the laser cavity. L naught is equal to capital L plus n minus 1 into small l is the optical path length within the resonator. L is the length of the active medium. N is the refractive index of the active medium rod. VA is the volume of the active medium. Sigma E is the stimulated emission cross section. Tau C is the lifetime of the photons, and gamma is the total loss per pass in the resonator. For critical pump rate, we set dn over dt is equal to 0. Phi is equal to 0. That is the initially no photon was present. This is what we are assuming. And the derivative of the population inversion with respect to time is equal to 0. Then we need to set n is equal to nc in equation number 111.7. That is from the previous slide. We need to put these values in equation number 7 of the previous slide, and we shall obtain this expression as shown in equation number 112.2. So let me show you the previous equation from the appendix. That is equation number 7. This is equation number 7, which will give you the rate of change of the population inversion with the time for a quasi 3-level laser systems. So in order to find the n to be critical n, that is the NC, we need to set dn over dt equal to 0, and then we need to solve this equation for the value of NC, which is given in equation number 111.2. So this will give you the value of RP, that is the pump rate. So the pump rate we have solved, we have set dn over dt is equal to 0 in equation number 111.7, and we have solved this equation for the value of critical rate. So the critical pump rate is equal to F times NT plus NC divided by 1 plus F times tau, where NT is the total population, that is the population present in the lower laser level plus the population present in the upper laser level, and NC is the critical population inversion. This NC value is given in equation number 1 over here, which we have calculated. F. Generally, F is much less than 1. And we can set 1 plus F equivalent to approximately equal to 1. Let's rewrite equation number 2, that is this equation, as critical pump rate, that is RCP, is equal to F times NT over tau plus NC over tau. So you see that in the denominator we have assumed the value of F over here, and we have divided the denominator to each term of the numerator. So you see that we have this term over here. So in equation number 2, we have changed 1 plus F equal to 1, because we have used this approximation that 1 plus F of the order of 1. So 1 plus F is equal to 1. So in the denominator, we have just only value of tau. So we are going to divide tau to both of these terms in the numerator. So we have the critical pump rate is equal to Ft into Nt over tau plus Nc over tau. Or we can write this as critical pump rate for a 3-level laser system, because this expression is for a 3-level laser system. So this RCP is for a 3-level laser system. So RCP for a 3-level laser system is equal to, for a 3-level quasi laser system, is equal to F into Nt over tau plus RCP for a 4th-level system, because Nc over tau is the pump rate, is the critical pump rate for a 4-level laser system, and we have written this expression by labeling that this is for a 3-level system, which is equal to F times Nt over tau plus the critical pump rate for a 4-level laser system. That is, the critical pump rate for a quasi 3-level laser is increased over the 4-level laser system by the addition of the term, which is F into Nt over tau. In case of uniform transverse pumping by a diode laser, we have the value of Rp, that is the value of pump rate for a uniform transverse pumping due to a diode laser, is given by this expression. So Rp is equal to eta P times PPE, which is the electric power to the pump, divided by A into L into H nu P, where A is the area of the active medium rod, L is the length of the rod, H is a Planck's constant, and nu P is actually the pump frequency. So we can equate equation number 2, that is equation number 111.2, and equation number 3 to write down this term, that is X is equal to Rp, ratio of Rp to RCP is the same as the ratio of PPE to P threshold. So this is the threshold pump power in the denominator, and you can say that X, the threshold pump power, can now be obtained as, you see that our objective is to calculate P threshold. So we can write the P threshold value over here. So what we need to do is that we have the value of Rp from equation number 3. We have the value of RCP from the above relationship, that is from equation number 2. So we have the value of Rp and RCP from equation 2 and 3. We can use these values over here, and we can see that PPE will be cancelled out, and then we can solve this equation for the value of P threshold, and this value is given in equation number 4. So P threshold, that is the threshold pump power, is equal to H nu P over eta P into tau, multiplied by the term which is F into Nt plus Nc within the parenthesis, multiplied by A into L, and then the denominator is 1 plus F. To make this expression independent of Nt and Nc, we substitute the values of, so you see that we wanted to write this P threshold power in to be independent of Nt and Nc, and for that one we are using F is equal to sigma A over sigma E, and Nc from equation number 1, and B is equal to sigma A times Nt times L over gamma. So we are using the value of B, we are using the value of F, and we are using the value of NC from equation number 1. So using these three equations, the equation number 4 can be written in the following form. So P threshold is equal to gamma times 1 plus capital B divided by eta P, and a term which is h nu P over tau, and another term which is capital A over sigma E plus sigma A. Let n naught represents the continuous wave inversion above the threshold. And you know that at the threshold or above the threshold, the value of n naught will be the same as value of nc. So let n naught represents the continuous wave inversion above the threshold, and phi naught represents the continuous wave photon number above the threshold. Then n naught is given by. So this n naught is equal to the same value as nc, and that is equal to gamma over sigma E into L, which we have derived earlier. And phi naught can be obtained by setting dn over dt equal to 0 in equation number 111.7, which gives this relationship. So let me show you equation number 111.7 from the previous slide from the appendix, in which we are going to set dn over dt equal to 0. That is, this is the equation. This is the equation number 111.7 from the previous slide, and we have dn over dt on the left hand side. So we are going to set this derivative to be equal to 0. And then we can solve it for the value of phi. So you see that we have this equation. Except that we have introduced phi, instead of phi we have phi naught, and instead of n we have n naught. Because you see that under this condition, that when the inversion would not change with time, then of course we have the values which are the threshold values, or which are the steady state values. So we have used the steady state values of the photon, which is the phi naught, and we have used the steady state values of the inversion, which is n naught. So all the n has been replaced by n naught, and phi has been replaced by phi naught. Now you see that in order to solve this equation for the value of phi naught, what we are going to do is that this is the second term, and we are going to divide this term by the value of sigma E, and at the same time we are multiplying this term by the value of sigma E. So sigma E will divide this term, and then we have sigma E over sigma E plus sigma A over sigma E. So this is 1 plus sigma A over sigma E, and sigma A over sigma E is F. So we can write 1 plus F. So what we, in order to find out phi naught, we are dividing the whole equation, all the terms in the equation, by 1 plus F. And then we shall get this expression that phi naught is equal to V over V divided by C into N naught into sigma E multiplied by RP minus V over C into N naught into sigma E, and then multiplied by this term shown in green, which is F into NT plus NC divided by 1 plus F into tau. So you see that the term which is in green is nothing but RCP, which we have derived earlier. So I am replacing this term by RCP in the next, for the next step. And you know that there is another RP is present over here. So I am dividing this RP with the value of RCP, and at the same time I am multiplying with the value of RCP, so that I can take RCP as a common term from the second term and the third term. So RCP is shown as a common term, and the parenthesis contains RP over RCP minus 1. And you know that we have defined our ratio of RP to RCP as X. And then we can write this step, that phi naught is equal to V over C into N naught into sigma A multiplied by RCP multiplied by X minus 1. And if you reinsert the value of RCP, which we have done over here, then this expression will be the final expression. So phi naught will be equal to V over C into N naught into sigma E multiplied by F into NT plus NC divided by 1 plus F and this multiplied by tau. And then these terms are multiplied by x minus 1. So this is the rearrangement of terms, that is phi naught is given by V over N naught, because here we are using the value of F, which is sigma A over sigma E. In the last step we are replacing F by its value, which is sigma A over sigma E, and then we are rearranging the terms, and then we finally get phi naught is equal to capital V over N naught divided N naught into sigma E plus sigma A multiplied by C, and then the term is F into NT plus N naught over tau, and then another term is x minus 1. So this will give you the steady state value of the photons in the cavity. Here we have used x is equal to Rp over RCP, which is also equal to PPE over P threshold. So x is actually the amount by which the threshold exceeds. To express phi naught in another form, we use capital V is equal to A times capital L naught. F is equal to sigma A over sigma E, and we introduce capital B is equal to sigma A times NT times L over gamma, and we are using this relation from the previous results. NC is equal to N naught is equal to V over VA into sigma E into C into tau C, and this is equal to gamma over sigma E into L. And we are also using tau C is equal to L naught over gamma C. So using all these terms in the previous equation, that is in equation number 7, and rearranging the terms, we get the equation number 8. So phi naught is equal to A times gamma, and within parentheses we have 1 plus capital B. This whole numerator is divided by sigma E plus sigma A, and then outside this square bracket we have a parenthesis containing tau C over tau, and then another parenthesis containing x minus 1. If the beam cross-sectional area is AB, so AB is actually the beam cross-sectional area is smaller or equal to A, then we can write this one. So here we are assuming that so we can write phi naught is equal to AB. That's we are replacing A, which is the cross-sectional area of the active medium rod, by the value of AB, which is the cross-sectional area of the beam. So AB times gamma times 1 plus B divided by sigma E in plus sigma A multiplied by a parenthesis containing tau C over tau and multiplied by another parenthesis containing x minus 1. The optical power from mirror 2 is given by P out, that is the power out from the mirror 2 is equal to gamma 2 times C over 2 L naught multiplied by h nu multiplied by phi naught. Phi naught is the number of photons in the cavity. H nu is the energy of each of such photons, and this is the fraction that we have discussed in one of previous slide. For example, in slide number 108.15. And gamma 2, you see there is the loss through the mirror, is the logarithmic loss through the mirror 2. You know that we have found the value of phi naught. So we can insert the value of phi naught over here, and then we can calculate the output from the mirror 2. So substituting phi naught from equation number 9 into equation number 10 and replacing x by PPE over P threshold and tau C by L naught over gamma C, we obtained this relationship. That is the power out from mirror 2 is equal to square bracket containing AB times 1 plus B divided by sigma E plus sigma A, then another parenthesis containing h nu over tau, another parenthesis containing gamma 2 over 2, and another parenthesis containing PPE over P threshold minus 1, as this is shown in equation number 11. So you know that the laser slope efficiency is given by eta S is equal to the rate of change of output power with the input electrical power to the pump, that is dP out over dPPE. So if you calculate this derivative from equation number 11, you can label that one as n eta S. So eta S will be equal to this term. Only the last term will change during the derivation, because the derivative of this term with respect to PPE is 1 over P threshold. So the derivative of 1 is constant. So we have this relationship because the rest of the terms are independent of the value of a PPE, so they will stay constant. So we have eta S is equal to square bracket containing AB times 1 plus B over sigma E plus sigma A, and then we have a parenthesis H nu over tau, another parenthesis gamma 2 over 2, another parenthesis now containing 1 over P threshold. You see that we in equation number 5, that is in this equation, this is the equation number 5, and we have the value of a P threshold, that is the threshold pump power from equation number 5. We can use this equation over here, that is P threshold can be used over here, and we can write eta S in the following form. So eta S is equal to eta times P, where eta P is the pump efficiency, and then the rest of the terms are the same, may be rearranged in a slight bit form. For example, this is gamma 2 over 2 times gamma, then we have H nu over H nu P, and then we have AB over A. So these are actually the 4 terms, eta P times this parenthesis times this parenthesis times this parenthesis. And this is the eta S slope efficiency on the left hand side of equation number 13. So you see that we have noticed that when we discussed a 4-level laser system, we found that this relation was the same as in equation number as for a 4-level laser system. So we have derived this for a quasi 3-level system, for a quasi 3-level laser system. So we can say that the eta S, which is the same for a 4-level laser system. For that one, you need to see equation number 109.10. For the same expression for a 4-level laser system, the eta S for a 3-level laser should be different from its 4-level counterpart, because the lower laser level in a 3-level quasi laser system is not a fast decaying level and may be a cause of increase in the loss due to photon absorption by stimulated absorption by the non-zero population present in the lower laser level. You know that in the quasi 3-level laser system, the lower laser level is not an empty level. So you see that the population in there can reabsorb the emitted photons. So the photons which are emitted through the stimulated emission can be reabsorbed through a process known as a stimulated absorption. But this stimulated absorption increases the population of the upper laser level and thus compensates the loss. Thus, eta S for a quasi 3-level system is identical to 4-level laser system. So you see that this completes my lecture on question number on slide number 112. So you see that here I have given for a 4-level laser system the value of eta S from equation number 109.10 is listed over here. So this is the end of slide number 112.